welcome every student to this session. This is experimental section from Physics 1 for the subject of laboratories in Physics 1, 01420113. This is experiment 3, kinematics and dynamics of one-dimensional 1D motion. Department of Physics, Faculty of Science, Kasetsart University. I'm Sarasat Panpak. I'm the host today. There's three main objectives for this experiment. Firstly, to observe motion of an object and learn how to apply the law of motion to explain the corresponding motion. You will investigate the motion of the object and then try to apply the knowledge of the kinematics like position, velocity, and acceleration to understand the Newton's second law of motion. Secondly, to learn how to do the experiment for calculating an acceleration of the mass and later compare it with the known value of the acceleration. So by this, you will use all those investigate parameters and try to calculate and get out the acceleration so that you can compare with the fact value of the acceleration, which is in this case is the gravitational acceleration. So it is the third part of the objective to find the Earth gravitational acceleration. So with these three objectives, you will learn through this experiment. So we're going to focus on two parts. First part is mainly about the kinematics, the motion of the with the constant acceleration on a slope. So with this section, with this part, you investigate the motion of the object, which is the guider in space and time. By that, you can acquire the position to understand more about the displacement and calculate the velocity, also the acceleration of the guider. From the next part, on the part 2, you will learn more about the dynamics using the law of motion of Newton's second law. And then you can investigate the causality of the glider motion, which is the gravitational force dragging another glider particle to moving along the air track. So for the first one, we will focus on the motion with a constant acceleration on a slope. So let's start with the introduction. For example, this orange slide down and stop at some point due to some friction. If the friction force equal to the pulling force, which in this case is mg psi theta, is from the gravitational force, and have it on the plane that this orange slide down. So in balance of these two parts, it can cause this object stop. But for the friction-free system or frictionless slope, in this case, we use air track for get rid of the friction. The orange can slide down with a constant acceleration, which is d psi theta. So by this, you will see the relation of how this object change position. So what is represented here, we have different position like x1 and x2. The change of the position causes the displacement. So with this displacement, originally orange have the initial velocity, and it can change to the final or terminal velocity according to the acceleration. You can use the equation of motion, like this is one of 4 or 5 equations that you learn in the major physics course already. So with this relation, you will find the terminal velocity according to the initial velocity, acceleration, and the displacement. So the parameter that we're going to use in this experiment is the displacement for the terminal velocity. So if we acquire the position of this organ from different, and we can plot the displacement against velocity. So the slope of this relation equal to 2a can be investigated. So by this you can compare the experimental observation of acceleration to what you have known already, and you prove from the Newton, the second law of motion. Then you will see this part further in the second part. So by knowing a from the slope and compare to a that you know a is equal to g sine theta, you can find the percent of errors for this observation. So what is in the experiment? So I will introduce the equipment, the tool that we are involving. So firstly is the glider with the opaque barriers. So with the length d, this is what you use for represent the distance that this glider go through the photogate. The photogate gonna count the time that this black opaque barrier go through and block the light from the photogate. The time that this has been blocked is going to record by the time counter. You're going to read this time out, represent as a t, and then have the d. When you have the length and time, you can find the velocity at this moment. So this is the way to find the terminal velocities. And the third one is the air blower unit with the air tracks. So without the air blower, the air track will have like a load of resistance. But when you turn the blower on, so this track become the resistance free. So you have the frictionless slope for when you open the air blower. For the first part, we would like to investigate the particle that moving along the slope air track. By doing that, you have to rise the air track and create the slope. So using this for raising the air track up. By introduce this part, you will have the angle or triangle shape like this, and you will know the force that introduce this glider to moving is mg sine theta. That's why you have to know the theta. By doing this theta, you have to measure the height at two different points, and you divide by the different position. By that, in this small angle, sine theta is equal to tan theta. That's why you use this to calculate the theta as an argument. After you know the angle of this slope, now you need to mark the position of your photogate. The photogate can be anywhere, but I recommend at 80 centimeter point. So the way you define the position is when you use the glider and reach to this photogate and have the first event that photogate read out block. So you mark this point as x1, and you mark the x0 as the position that an air blower tube get in. So that this is kind of like 0 centimeter position and this 80 centimeter position. A part of this initial setup, you have to understand how to use the time counter as well, because you will read out the time that the glider go through the photogate, right? You have to set the right function and mode. So first you have to set the mode, and the mode should be like this. You click on this mode to have like a pulse type of the mode, and you have this type of biac readout. Second, make sure you reset by pressing this button every time when you have the glider pass through the photogate, because every time when it's passed, it's gonna have some readout. Make sure you reset every time. Finally, for the timer, Another thing is make sure you use the right unit in second and read the time record out of this panel. When you have the digital readout like this, you have to take all the digits out because this is the precision of the machine that you has been used. This is what I would like to explain about how you find the terminal velocities by using the photogate. The scenario is like you have the glider move through the gate. This is what is happening in the first event. So the time counter gonna take as a T zeros, and then when this black opaque barrier move through with this lane, the time gonna change to the final end. So the change with the time is what this time counter readout. If you would like to find the terminal velocity, in comparison, it's like in the real life, you would like to measure the speed of the car, you have the reference like a tree line and the time that the servant cam has been recorded. So with the length or the size of the barrier or the length of the car with the time that you record, so you can find the terminal velocities. So this is in comparison to the same situation that you would like to observe. And this is the photogate and the example. In this case, you will record the time from the time counters. And what is the variable parameters? The variable parameters is the displacement. So the displacement is what the position that you release the glider to have the terminal velocity at the photogate. So you did set up the photogate position as a X1 already. So in this experiment, we suggest you to observe the displacement from 20, 30, 40, 50, and 60 centimeters. So you will move the glider away from the photogate at different position. So with different displacement, you will have different terminal velocity. According to this relation, you will see the trends when you apply for the further investigation. So this is the example of releasing the glider at the position like 20 centimeter away from the photogate. You see this number we show out and record it. So with different position or different displacement, you do exactly the same, but make sure reset every time before you release the glider. So just move it away from the glider at the right position and release it. For the time sheet, you have to repeat each of these displacement for 3 times. So please do as the suggestion. So this is what gonna count for your score for the final. So after you record all the time point or the time point with different displacement or release position, you get different terminal velocities. V square can be plotted against the delta x displacement. So you find the linear relation, and this has been stated before. It's equation of motion of this v square equal to u square plus 2a delta x. By this, you will find the slope of the trend as 2a. It can be found easily after that. If you like to compare with the fact value, as I stated before, g is what you already know, gravitational acceleration. So you can sub g or change this form to the g, compare for the percent of errors. This is an example of the record on the data sheet. Make sure you fill in all the space and you have to repeat 3 times for the time average. And after that, you will find V and V square. For the graph plottings, you're allowed to use the graph sheet or using the Excel for plotting it. And you have V square against delta X in comparison. Finally, you're going to get the slope and answer all these questions. This is the first part of this experiment tree. The second part is about the dynamics. You will use another drag force and pulling this glider along the tracks. So what is the second law of the Newton? It's mainly about the force. If you have the force exert to the system, in this case, this bull pulling the car with the force as a tension T, this makes this car moving with the acceleration. This is the key of the second law, Newton's second law of motion. So when the bull keep pulling, it can drag to some point. Now bull is falling off the cliff like this. This is the second part of the experiment in comparisons. So with the frictionless air tracks that we have in the system, we can observe what is happening here. So the main force is due to the weight of the bull now. It's tension, yes, but tension is directly linked to the weight of the bull. So by this relation, we can use for calculate the acceleration that dragging this car. So we can break the free body diagram and see the relation of it. So by this you can see that the tension is equal to mass of the car with the acceleration, and from the bull itself you have the mass of the bull dragging down. This is the weight of the bull minus with the tension with the acceleration on the bull moving downward direction. So this car has no engine, it's completely breakdown. All the forces come from the weight of the bull. So with this relation, you can find the correlation between the gravitational acceleration to the acceleration of the car or of the system. And this parameter is about the mass of the bull and the mass that you include with the car and the bull together. So from this relation, you will apply with the equation of motion, the one that you already used. And this acceleration, if you sub in, you will find the relation between the terminal velocity of this car and the mass that you're using for dragging this car down. So this is, if you plot this v square and m is kind of like a not a linear relation. With this definition, you can find the slope, and g can be extracted from the slope in terms of the experiment, like this. But by doing the experiment, you will get a bigger picture about what is happening in terms of Newton for the dynamic investigation to the kinematic parameters that we can record. So in the experimental part, we mostly use the same type of equipment, but we add the hook and string for pulling this glider by the M2 weight. And also this glider moves through the photogate as well. So for the setup of the experiment, you have to move the photogate a little bit closer to the pulley, which is attached to the end of the table. So let's make this position as the X1. So X1 is the position that the glider initially block the light of the photogate and turn on the light, right? So it's first when it's about to read, the the barriers out, and you fix the displacement. This time we're not going to vary the displacement. We're going to vary the mass that weight on the glider and also the mass that weight on this hook M2, so that we fix the delta X to 50 centimeter. You move the glider away from the photogate around 50 centimeter all the times. And make sure you measure all these objects because mass can be varied. Right? Measure the glider without the loading mass yet. Sorry. Measure the hook without any loading weight, and make sure individual weight is about 10 gram or 100 gram. 10 grams, sorry. There's several experiments you have to do through this part, but make sure you understand the step of the experiment. So for the first experiment, you load all these weight to the glider. So you have the total 10 pieces of this weight plus 100 grams and no loading onto the M2. And you slide this away further for 50 centimeter before release it. And you release it and repeat for 3 times. Read out the times as a recording. 2 times, not 3 times in this part. And you will find the terminal velocity with the same method that you used in the first part. And for the further experiment, like number 3, number 5, you get the mass out each like 20 grams round and fix the position, the displacement to 50 centimeter. So keep recording this until you remove all the load mass to the hook and measure the times. By this, you can compare the relation of the weight mass to the terminal velocity. So let's say this is an example of the experiment. For the number 1, there's hints of the weight on the glider and no weight on the hook. You can see it's slowly moving. Make sure you reset this every time before you release it, right? Don't worry about the string initially. It can be like drop, not tense, but in the final, you will usually the tension come back. For the experiment number 2, you get off, you take off the 2 uploading weight to the hook, and then you release. You can see it's quicker, much quicker. This is how you compare the terminal velocity on the first condition to the second. By doing this experiment, you will have all the terminal velocity from all this experiment, from the weight you load. With this, you can plot the relation. And what I said already, you have the terminal velocity against the mass of the loading weight. With this relation, you will find the constant or the slope out of it. And the slope is related to the g of the gravitational acceleration, this one. You can find this and compare to 9.8 net per sec squared as a fact value. So by that, the percentage of errors can be observed. So this is the example of the record sheet. And you can see from the list of the experiment, this is what you not taking any load out. So 100 gram on the glider, you take out like 20 each, 20 each, 22 is all load to the hook. And you note the M1 as the mass on the glider, M2 is the mass on the hook. T1, T2 is the repeat of observation. You have to repeat. You need to repeat for the investigation, and you do average. Finally, you got the time average, and you know the T of the the barrier, you can find the terminal velocity. With the relation of terminal velocity and the loading mass, you find the linear relation of the terminal velocity. By that, you can find the g as the gravitational acceleration. That is everything for this experimental second experiment 3. Thank you so much.